Okay, so I wouldn't go back, to the previous discussion. We'll take up from where we left off. The point is we specify a regression model, and then we learned how to estimate it using the ordinary least square or the least square estimators. After estimation, we learned how to interpret our models and so on. We went through some assumptions, and then we talked about inferences, where you're able to make comments that and whether this variable, for example, enrollment, is statistically significant or not. So the take-home exam one of these, and you have the opportunity to practice these things. Today, I will take some data and we'll see how these things are run. I'll do it in Stata. You can do it in Excel, whatever program you are comfortable with. So we did inferencing, we talk about the R-square. And this after, I want to start by discussing why sometimes the signs of the regression coefficient could be wrong. For example, you're expecting this coefficient to be positive right here. Okay, I've just seen some question. I will come to that. Let me make some progress. So I'm looking for my pen. So maybe you're expecting this variable to be maybe the effect of years.
Multiple regression analysis.
What's that?
John joining there last class, joining.
Who is John, so that I deduct from his course since he doesn't come? Okay. So maybe you're expecting this coefficient, the effect of years on salary, maybe you expect to be positive, and then it turns out to be negative. That's what we mean by regression coefficient having the wrong sign. So what do we have here? What is that sound? Let me just mute that sound. Mute participant upon entry, yes. And then once again, play sound, no. Don't play sound, okay. All right, so let's keep going. I hope you can hear me, folks. So that's what I mean by regression coefficient having a wrong sign. The coefficient may have the wrong sign if the range of some of the regressors is too small. I've talked about range here, right? If you want to explain the impact of education on people's salary or wages, you need some variation in the wage, in the education data. So if your regressor doesn't vary much, the range is too small, it could cause that. It causes you to have a negative sign, or a wrong sign. Okay, and that is so important, right? You may mislead policymakers if the variable is related in a negative fashion, but you say it's related positively. Okay, so it's important. Important regressors have not been included. Yes, if you don't include some important variables or regressors, you may end up having a wrong sign. One of my professors said, who taught to me my master's program, he regressed let's say school fees. He regressed university enrollment on the school fees. So what do you expect will be the sign? How are they related? University education and then the school fees. The higher the school fees, the lower the enrollment, or the lower the school fees, the higher the enrollment. So you expect a negative relationship between university enrollment and school fees, okay, or tuition fees. Okay, so that is the expected sign. I'm looking for my pencil here. So you probably expect a negative relationship between university enrollment and the fees people pay. In other words, the higher the fees, the lower the enrollment, and so on. So that's what you expect a priori. But my professor said when he did it, he got a positive sign. that the higher the school fees, the higher the enrollment. They use data from the US. So that was an anomaly, really wrong. We were not expecting, you wouldn't expect a positive relation between school fees and university enrollment. So it turns out that he had omitted an important variable. So that's what we mean by if you omit important regressor, if you do not include important regressor, you may have the wrong side. Now, what was this important variable in his case? It was the scholarship. Whether a student enjoyed some scholarship or not, that variable should have been included. So it turns out that almost every student in the US has some scholarship somehow. Okay. Even here at Ashesi, I was told today 48% of the 1,200 have some scholarship. So you see, that's huge, about 48%. Same in the US, almost everyone has some form of scholarship. So it turns out that the higher the school fees, it doesn't really cause enrollment to reduce. The higher the fees, you will see the higher the enrollment. So that's why my professor saw a positive relationship. So when he included another regressor or variable, which is called the scholarship status, whether a student receives scholarship or not, immediately he included that variable, then the sign became negative as expected. So he was able to correct a wrong sign from positive to negative. And it was wrong because he did not include an important variable. Okay, I hope that makes sense. And you could have the wrong sign if multicollinearity is present. Multicollinearity occurs when two regressors are highly linearly related. If two regressors are highly related. So in this example, if you have these two variables, for example, years and games year, if these two regressors are highly linearly related, let's say correlation coefficient of 0.9 or even 0.85 and so on, they are highly related linearly. And it turns out that, you see, when two regressors are highly related, the information in one is almost contained in the other one. Okay. There was a research I listened to somebody and he said he had two regressors. That was like, were you scared you would get COVID? Then another one, did you get COVID? So yeah, you might find that those two regressors, were you scared you would get COVID, or were you exposed to COVID, and then did you get COVID? Those two variables are likely to be highly related. Almost all those who got COVID were once exposed. Okay. Please hold on just a second. So that's sorry about that. So that's the idea of multicollinearity. If these two regressors or any linear combination, whatever, if two regressors, three or more, are highly linearly related, we say there's the problem of multicollinearity. Okay, so there is another example I can give. If you have two variables like the size of a house and the number of bedrooms. If you have two regressors, like the size of a house and the number of bedrooms, these two are highly related. If a house is big, very big, it's likely the number of bedrooms are many, and so on. So if you have regressors that are highly related, the idea is the information in one can be obtained in the other. So one becomes redundant, but it affects the other one, and it can weaken your results. So that's what we mean by multicollinearity. Okay. And then there could be computational errors. We are lucky we are using software packages and so on. But if you were manually. In the past, we're manually computing these things. If you are doing it manually, you go have the wrong signs. Okay, so that's it. Let's move to something more interesting. There's something last time we learned about R square. Today, I introduced what we call the adjusted R square. Very briefly, adjusted R square is supposed to, this is the formula of, where is the adjusted R square? Right here. So last week, I think we studied, we discussed the R square. If you erase these guys, if you erase this here, this denominator right here, and you erase this, what you are left with is the R square we learned last week, 1 minus SSC over SST. How much of the total variation in the dependent variable is explained by the independent variable? That's the R square we learned last week. But that R square last week that we talked about last week, it can go up artificially. Okay, let me try and go back and see for the sake of those who probably weren't here. Okay, so take this example here, right here. For example, we report that what 58%, right over here, 58.5%, you multiply by 100, 58.5% of the variation you see in log crime is explained by the variation in log enrollment. In this example last week, I said we wanted to see how enrollment in the university affect crime on campus. And we find that the crime we observe on campus, 58.5% of it is explained by the number of student enrollment. In other words, if enrollment goes up by 1%, there will be 1 percentage point, there will be 127 percentage point increase in crime on campus. Okay, so this R square here tells us 58.5% of the variation or differences in crime we observe on university campus can be explained by the enrollment numbers. So that's the idea of the R square. Now we tell that this R square has a problem. Okay, if you keep increasing the regressors, this is enrollment, you can add gender, maybe add another variable called gender of the gender balance on campus. I'm just making up a variable. Okay, even if you add irrelevant variables, this R square goes up. So this R square can go up artificially. So it might not be a good indicator of how the model is faring. And that is why we try to adjust it by what we call the degrees of freedom. Okay, who is that? Let me mute him. Okay. Oh, I can't find him. Okay, so that is why we introduce the adjusted R square, which is adjusted by the degrees of freedom. In other words, a variable only contributes to the R square if it is useful. If you add irrelevant variables, the adjusted R square will not go up. So this is a better way of checking the fitness of your model, whether your model was able to explain variations in the dependent variable. So that's the idea of the adjusted R square. You can show mathematically that it can also be written this way, okay, which I don't have time to show. So most of the time, rely on the adjusted R square rather than the R square, because the R square can go up artificially. If you throw in any variable, R square goes up. But adjusted R square only goes up if you include a relevant variable. Okay, enough said about that. Let's go to something more interesting, qualitative information or indicator variables. Okay, so far I've talked about quantitative variables. Okay, variables that are quantitative, like wage, education is measured 1, 2, 3, 4, 5 positive integers, so that is quantitative. Okay, and then we've talked about amount of fertilizer included, 1 kilogram, 2 kilogram. These are all quantitative. Sometimes you might want to study the effect of variables that are qualitative in nature. Qualitative, for example, gender, race, industry. Somebody's gender is male or female. That variable male or female is not coming in a quantitative manner, it's qualitative. Okay, nominal. Then what is your race? Black, white, and so on. These are also not quantitative. So how do you capture? Because the regression framework was actually designed for quantitative models of variables. So we want to study how you can include or capture the effect of qualitative variables, also known as indicator variables. Okay, a simple example, my friends, here is gender. So somebody wants to see the average effect of gender on people's wages. Okay, whether gender has an influence on people's wages or not. Okay, those who are interested in studying discrimination against women in the United States, thought about checking out the effect of gender, whether male or female. So you can have a model of wage regress on gender, which is here female, and education. Okay, education is already known to be measured as a positive integer. Gender here is called female. You can call it gender, you can call it male. Here is being called female. Okay, so over here, because gender is qualitative, you give it some numbers. Okay, you give it some numbers that make them easy to interpret. So here we assign the value of 1 to females and a value of 0 to male. It's up to you. You can switch them wherever you want. You can switch them. So over here in this discussion, we have female being equal to 1 and male equal to 1. I will show you in Excel shortly. Okay. Yeah, so this is it. So this is the dummy variable right here. Here. This female, all the females in the data will be given a value of 1 under this variable called female. I prefer to call it gender, but no big deal. Okay. You can call it whatever you want. Just know how you are categorizing it. Okay, so this variable is equal to 1 for all persons that are women in the data and equals to 1 for all men in the data. Okay. So think about it. So over here, we can think of the slope on education like this. For women, when a person is a woman, or for women, this is what we have. It reduces to wage. I'm going to put 1 here, okay? I'm going to put the number 1 in place of this because I'm talking about women. And this variable is equal to 1 for women and 0 for men. Usually we make it 1, 0. That makes it easy to interpret. And therefore, you categorize in terms of percentages. Okay. So that's why we're using 1, 0. It's easier to interpret. And mathematically, it becomes tractable. Okay. So wage here for women will be equal to what? Beta 0 plus delta 0, because I've put the number 1 in play in terms of this. I've put 1 here because I'm thinking of female. Every female gets the number 1 here. So beta 0 plus delta 0 plus beta 1 education. Education. Then you can add the error term. Then for men, what do we have? When we talk about men, the equation becomes wage is not different from beta 0. Over here for men, I'll put 0 here because this variable is defined to be equal to 0 for men. Beta 0 plus beta 1 education. I've put 0 here. Beta 1 education So you can see the difference between the two equations is delta zero. One of them contains delta zero, one of them does not. So you see the difference. If you think of this as an intercept, right? So look at the difference between the woman and the men. Because we define woman to be equal to 1, the delta 0 survives. And because female is equal to 0 for all men, this variable is 0 for all men, we lose the delta 0. So the difference between them is just the delta 0. That's why we interpret delta 0 as what? The wage gain or loss if a person is a woman rather than a man holding other things fixed. Okay. So this delta 0 means women get delta 0 more than men. That's all. Because so as you can see, the difference in these two equations, delta 0. And think of delta, this, so the intercept here is this, and here the intercept is just that. That's why the next slide, you will see straight lines, you see. So beta 1 is the same, so the slopes are the same. They all look parallel, but there's difference in intercept. The women start here and the men start here. Okay, so the women are below. That's why some people would think of discrimination. That being a woman alone just means you are starting from the bottom than men. So that's what people used to say there is discrimination in the United States. So, but that's the idea. So most importantly, you must know how to interpret the coefficient of the dummy variable. So female here is called a dummy variable. And so delta 0 is what? How much women make, okay, more than men. And by the way, the category assigned to 0 is called a base category. And the one which is equal to 1 is a reference category. So you interpret the dummy variable, you compare to the base category, and we'll see more, okay, very soon. So the comparison, so delta 0 here means that females make delta 0 money on average more than the base category, which is men, okay, the one which was assigned 0. Okay, here, because there's the notion of discrimination, we think that women make delta 0 less than men on average, okay, basically. Okay, so there is something called dummy variable trap. Please stop me and ask questions anytime. Dummy variable trap means something similar I said last week, that we don't want perfect collinearity. We don't want perfect collinearity. If you remember, I spoke about that and show you two simultaneous equations which cannot be solved because of this problem of perfect collinearity. Because of that, you cannot include these two variables at the same time. So watch here first. You either go with this equation here. You either, where's my pencil? You either go with this here or you go with this one. That means both of them here, you cannot put both of them in the model. Both of them cannot be in the same model because they represent the same thing. There's perfect collinearity. If a person is not a male, he's a female. So you cannot have these two variables. This one will give 1 to female, 0 to men. This one will give 1 to men, 0 to female. They have the same information actually, and they are perfectly collinear. So you cannot have both. The model cannot be estimated. So that's called a dummy variable trap. So what does this tell us? Whenever you have two categories in a variable, or people say 2 levels, that's just a 2 levels. Gender has male, female. So you create the dummy for only one of them and use the other as a reference category. That's it. Do not include both, okay? Otherwise, you fall into what we call the dummy variable trap. If I'm supposed to represent all the months in the year, January, February, March, you have to leave one of them out as the base category. You cannot include a dummy variable for Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. No, there are 6 days in a week. If you want to see the effect of each day, you include a dummy variable for only 6 of them, and you leave one out. That one you leave out is your choice. Totally up to you. The one you leave out becomes the base category that you compare to. So you say, oh, assuming you left Sunday out, then the coefficient on Monday is 20. Then you say, oh, Monday sales are 20 more compared to the base category, which is Sunday, and so on. So that's the idea of a base category, how we interpret dummy variables, relating them to the base category. And that's the idea of the dummy variable trap, which you must take cognizance of. So please feel free and stop me anytime. Okay. So over here, look at the interpretation of this model right here. The interpretation says what? Our model has been estimated and there's a negative coefficient, which people say people attribute to the discrimination. So look at this. Holding other things constant, that means all the other regressors. Holding them constant. Women here. Holding all things constant, or the other regressors fixed. Women earn $1.81 less than men per hour. Because of the negative, that's why we say less. So females or women earn 0.181 less than the base category, which is men. Okay, which some people might attribute to discrimination. Okay, women earn $1.81 per hour less than the base category, which is men. And our model explained 36.4% of the variation in the wage. Okay, all these variables, 1, 2, 3, 4, that's our regressors, together explain 36.4% of the variation we see in wages. And we say that when you do this, it doesn't necessarily mean there's discrimination. It doesn't necessarily mean there's discrimination. It's possible that men are actually productive than women. We are just saying be careful. This does not actually mean discrimination unless you have done more to explain this negative relationship. Okay, being female may be correlated with other productivity characteristics that have not been controlled for. Okay, so it's possible that nobody is discriminating, but women are not seen or do not work productively as men. Okay, and again, women too may not find themselves in highly productive sectors. And so the average man may be seen to be okay than the average woman. Okay, if a man and a woman have nothing to do, the man is likely to have some money earlier than the woman. If you are going to clear some goods at the Tema Harbor, you just call the boys that, hey, let's go. If you are going to offload something from a truck, you call the boys, right? Not the women. And so men will usually have those opportunities because the guy thinks the men can help him lift the couch, refrigerator, all those German goods. So the average man might likely make more than the average woman. So it might not necessarily be discrimination, but hey, there's a lot of discrimination. There's a lot of discrimination in the US. Okay, those of you who are interested, you can check out a paper on discrimination in the US labor market. One of my favorite papers in graduate school is called, you can read it, it's not much, you can just look at the abstract. Anybody with a phone can Google and let me see if I have the name right. The paper says, are Emily and Greg employable? Are Emily and Greg employable than Lakeisha and Jamal? It's a paper on labor market discrimination in the United States. Are Emily and Greg? Okay, if somebody has a phone, you can Google and let me know what exactly the title is. By something like, are Emily and Greg employable than Lakeisha and Jamal? Lakeisha, are Emily and Greg employable than Lakeisha and Greg? Okay. So in the United States, whenever you hear names with sha, the person is likely to be an African American or a black person. Okay.
Yeah, I've seen it.
Yeah, what's the title again?
Emilia and Greg more employable than Lakeisha and Jamal.
And Jamal. Do you have the abstract? Can you read? Very interesting paper.
Okay, let me just open it. Let me open
my
that.
favorite paper in graduate school about labor market discrimination. These guys from, I think, Boston, they did fake CV. Okay, fake CV. So in the US, when you hear Lakeisha and Jamal, anything Shasha is likely to be a black person. And Emily is likely to be a white person. So you know Moisha, Lakeisha, Maisha, all those Shasha, Kezia, and so on, Kayla, they are all likely to be black people. So if an employer sees the resume or the CV, a CV is called Emily, a CV is Lakeisha, the employer knows Lakeisha is black and they might discriminate. So this researcher sent fake CV, the same qualification they sent to the companies. They found out that Emily and Greg were getting interviews for job than Lakeisha and Jamal. These were fake CVs. Sometimes they even made Lakeisha's CV better than Emily. But still, the employers offered Emily the job. Emily got calls for interviews. Right? So that becomes a solid evidence of discrimination in the labor market in the United States. But a simple regression or a regression like this is not enough to claim discrimination. You gotta do more. Okay, so more on qualitative. Over here, I'll move to Excel and show you how we capture these things. So folks, look at this. We have somebody wants to see your marital status, effect of marital status on your wages. In this study here, you are seeing they want to check out the effect of your marital status on your wage per hour. So there are 4 categories of people. There are married males, married males, married females, single females, and single men. But you see, we didn't include a single man. You leave out one of the levels. There are 4 levels: married male, married female, single female, and single men. So this researcher chose to leave out a single. I told you, because of the dummy variable trap, you leave out one category and you interpret your results and compare to the base category. Okay. So I'm going to move to Excel and just show you, give you a flavor of how these dummy variables are coded. Okay, so I'm going to have an example of 4 people. 4 people here. Where is this Excel? Okay, it's still opening. So we'll have an example.
Yes.
Okay, please, can you see the Excel?
What I was saying?
Yes, we can see.
Yeah. The name, the wage, education, then married, female, married, male, married, single, female. So you leave out one category. In that example, they left out a single man. So this is how the data will look. If you have me here, Deborah, you know, I don't get paid much. Let's say I make 1,000 cedis a month. Education, PhD, maybe let's say 20 years of schooling. Am I a married female? No. Am I a married male? Yes. Am I a single female? No. So this is how the variables are coded. All those who are not married female will take 0, 0, 0, 0. All those who are married men will take 1, 1, 1, 1 here, and so on. So let me have my friend Perpetual, my colleague here, Perpetual. Let's say her salary is also 2,000. She's a senior lecturer. I'm just a lecturer. Education, also PhD. Let's say, assuming she did a postdoc, so let's say 22. Is she a married female? Yes, so she takes 1 for married female. Is she a married man? No, 0. Is she a single female? No. Okay. Then I grab 2 names from your list here. There is Sadat and Equia Ata. So we have Equia here and Ata. I'm assuming they are all single. So these are PhD students. They are not making much, but Equia is doing business, selling perfume. So let's say she makes 2,500 a month. She's now doing a PhD. She has a master's. So let's say 18 years of schooling. Married female, no. Is she a married male? No. Is she a single female? I'm assuming yes. Okay. So this is how we categorize them. Then Arthur is a single guy. So he is also sells mobile phones, carries from cycle to sell. He's a big guy, makes 3,000. He's master's degree holder. His master's was only 1 year instead of Equia, unlike Equia. So he's 17 years of schooling. Is he a married female? No. Is he a married man? No. Is he a 0 here? Is Arthur a single female? No. So he doesn't get 1 year because he is the single man, which we have left out. Anyway, so the category you leave out. So you see a variable here like this. We have 1 for married female and 0 for 0 otherwise. So this how is categorized, by the way, the dummy variables or the qualitative. So this is how we are capturing effect of marital status on people's wages in that particular study. I hope it makes sense. Any questions, then I'll move on. So the base category, we don't add it. Single men. If you add it, you fall into the dummy variable trap. And then let's say, assuming we added it, then I am not a single male. This is 0. Perpetua is not a single man, a woman. Equia is not a single man. Arthur is a single man, 1. So when you do that, you see that when you add all this is equal to 1. When you add all this is equal to 1. When you add all this is equal to 1. When you add all this is equal to 1. So all these 4 variables are perfectly collinear. You add them is equal to 1. So you have the dummy variable trap, and it's not possible. Your model cannot be estimated. Last week, you saw the share of the vote campaign expenditure. We said you couldn't include both because they added up to 100%. So that's a problem. So we omit 1, okay? It becomes the base category, and we compare. Any question here before I switch to the main slides?
Hello, sir.
Yes.
So you said when you assume you add the single, as is this single money,
Yes.
single, yeah. So it becomes what? Perfectly collinear.
Yes. So all these
Okay.
variables, they add up to 1. You see?
Okay.
They add up to 1. They add up to 1. The model cannot be estimated that way. Okay. They become collinear, perfectly collinear. If you have a matrix whose inverse cannot be found, it's something similar. A matrix that cannot be inverted, you are unable to solve for the coefficient. So that's what is going on. Okay. If you've taken linear algebra, it could be easy to explain. But last week I gave an example like this: x plus y is equal to 2. X plus y is not different from 2, and 2x plus 2y is not different from 4. 2x plus 2y is not different from 4. You cannot solve this simultaneous equation. That's what is going on. Okay. What I said is happening similar to this. So you see, because everything contained in this information, the first equation can be found in the second. There's no way you can solve for x and y here in this system. It's not possible. That's exactly what's going on, but it's in a different form. But that's a flavor. And so you cannot solve for the coefficient. You cannot solve. The program, software, Excel, whatever, has to drop one of them. So we help it by dropping it. You see, when you drop this one, you've broken the chain. When you drop this one, you've broken that chain. These ones will sum up to 1. This will sum up to 1. This will sum up to 1. But you've broken the chain here. This doesn't sum up to 1. And if you have about 100 data points, the chain will be broken for a couple of them, and you'll be fine. Okay.
So my question is, please. My question is, so if you meet, for example, the single man, or or maybe the 7 days, you omit 1 day, how will the rest give a fair representation and interpretation of the data? Since 1 day is omitted.
Yes, so that is the point of these dummy variables. The point, so you have left out what? 1 level. You said January or whatever. Yeah, we are saying that it is not, you've left it out, but it is represented somehow. It's represented somehow. You can still make comment on that January that you left out. That is why. So we leave it out conveniently, but where is the other one? Here. The only problem, look at the 2. Look at the 2 here. This is the equation for men. If you are here from the beginning, you know how I derive this. And this is for women, you see. Look at that. So this is for, the one who asked the question, are you familiar how we got these 2?
Not really.
Did you join late?
Yeah, I joined late.
Yeah, so that's why. But over here, let me just give you a flavor. Look at here, over here, this variable female is the same as gender. Okay, you put 1 for everybody who is a woman in the data, and 0 here for everybody who is a man. I've just demonstrated in an Excel. All women will take 1 here, all men will take 0. So here we are. So you see, for women, this is 1. So delta 0 will stay, will survive. For men, this is 0. So delta 0 vanishes. Here we are. See, you see that for men, delta 0 vanishes. For women, so you look at the difference. You see the difference is only delta 0. So although I left out a category called men, so over here I left out men and created a dummy variable called female, but I'm still able to tell, okay, that look, the difference is delta 0. That's it. So I say, oh, women make delta 0 more than men. That's all. So I'm still able to have some idea about the position of men. Okay. And actually, mathematically, this is much ado about intercept. This is much ado about intercept. Look at this intercept right here. This is beta 0. So this is just an issue of intercept. So if it is just intercept, then I have it for men. I don't have to create another dummy for them. So we haven't really lost anything. I can make inference on the position of men. The intercept is still captured. That's it. Okay, I hope that helps.
Yeah, thank you very much.
Excellent. Okay. Let's make progress. I have 9 minutes to switch to the examples. So, my dear friends, okay, this is something we'll talk about quickly. So, over here, we left out a single man. So, please look at the interpretation. Here, I will say married males make 0.213 more than single men. The category you left out is a single man. So you compare everything to the single man. Here, married females here make 0.198, because of the negative, I'll say less. 0.198 less than the reference category, single men. So know how to interpret this. My friends, because these are categorical variables, it is wrong. to say that if this variable increases by 1 unit, blah, 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 as we did last week. Last week, we said what? If education increases by 1 year, then holding other things constant, blah, 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 blah. Here, this is qualitative, right? So it's wrong to say if this increases by 1 unit. You are comparing to the base category, and that's very fundamental. If you go and do that, they will laugh at you somewhere. And don't mention my name that I taught you regression. So that's how we interpret the dummy variables or qualitative. Somebody may want to capture your region, your hometown's region, whether you are from Greater Accra or Eastern and so on. So we have 16 regions. You create a dummy for 15 and leave one of them out. And the one you leave out becomes the base category. And you compare all the results to the base category. And in financial economics, we have something called the January effect. Okay, that, oh, stock prices are usually higher in January than the other months and so on. You guys also know that sales in Ghana will be higher during Christmas, that's December, than other months. And somebody wants to capture the effect of months. So you can throw in the 11 months and leave one as a base category and say, oh, the sales in February are so and so less than the sales in December, assuming December were the base category. So sometimes people are interested in these categorical variables, their effect, and so this is how we capture them. It's fairly straightforward. Okay. There's one last thing I want to say, probably in 5 minutes. Then we move to the examples. Okay. Yes, Kwejo, the baseline question you just asked, yes, you can think of it because the one you left out actually becomes the base. Its intercept is the beta 0, which is the average in the population even before the study. So I can take that. That's correct. Okay. So we can have model adequacies. What consideration is given to the assignment of base category? I said you can choose anyone you want, but sometimes you yourself want to see how all the other months compare to December sales, Christmas. So you can just leave out the Christmas. Okay. Otherwise, there's no special way of choosing them. It's up to you. But if you want to have a reference period, for example, how do all the years compare to the COVID year? Then the COVID year 2020 becomes your base category. So it depends on your interest. Otherwise, whatever you choose doesn't affect your results. In terms of statistics, any of them works, but you might find an advantage in choosing one as your base category. And usually if you have data from 1990 to 2022, 1990 will usually be the base category, okay? Because it is the beginning. Then you can compare everything. Like, oh, the prices of mobile phone have been 20% higher compared to 1990, the beginning of time, and so on. So those will be some of the reasons why you may choose a particular year and so on. Okay, so the last thing, then we do some practical stuffs, and then we see you, you submit your take-home exam and so on. Please do it yourself and submit on time. Have a good grade. So after you've done all this, sometimes when regression is used for prediction, we like to see how well the regression has done. So I'll just give you a flavor on some of these things. You plot your residuals. Somebody was asking a question about residuals earlier on. So this is how they can become useful. You use your residuals to check the adequacy of the model. We call it model adequacy. Oh, the model I just fitted to the data, is it adequate? Am I able to predict the likelihood of somebody defaulting on a loan? Is the model adequate or not? Well, the computer packages can give you the residuals, okay? The residuals, for those who are not here, we say this is the actual, maybe somebody's GPA, and this is what we predicted for him, Y hat. So when we subtract it, we have a residual. This is the actual GPA, and we predicted he will get Y hat. The difference is the residual. The difference is the residual. So somebody's GPA, the actual GPA is equal to what I predicted he will get, the part I was able to predict, and the residual, what I couldn't predict. U hat is my residual. So this is equal to U hat, basically. And I just made Y the subject. Somebody's GPA or salary is equal to what I predicted he will get and what I was not able to predict. I was able to predict using his level of education, blah, blah, blah. There were still some parts I couldn't get right. So the part I was able to predict and the part I was not able to predict, the residual. Now, something I was able to predict and something I couldn't predict should have no relationship. This is the part I was able to explain, the part I couldn't explain. So these have no intersection. Therefore, when I have a graph of the part I was not able to explain and against the part I was able to explain, they should not be related. They should have no relationship. That's the idea of the graphs here, that this is what we expect. If your model did a good job, then when you plot residual against Y hat, there should be no discernible pattern. If you have a pattern like this, last week or two, I told you this is a pattern of heteroscedasticity. We don't want this. This means your model is not adequate. This also means your model is not adequate. This also means your model is not adequate. There should be no pattern when U hat and Y hat are plotted, because one is explained, one is unexplained. So they shouldn't have any systematic pattern. So this is what statisticians use to check the adequacy of their models, a graphical way. You plot residual against Y hat. Computers will do this for you. Your job is to interpret. This is what we want, randomness. Okay, there's no discernible pattern. This one means there's heteroscedasticity. I think I did a good job explaining heteroscedasticity to you. I will not go there again. This is also heteroscedasticity in a different form, where your dependent variable are fractions. For example, what proportion of your farm did you use fertilizer? So that Y variable is a proportion, is a fraction. So this is how heteroscedasticity shows up in such an analysis. And this will mean your model is not adequate. You look at this, it looks like a U shape, a curve. So maybe you need to include X squared in your model. Okay, maybe you included X in the model. You may have to include X squared because this model inadequacy test is telling you that there is some curvature, a U-shaped curvature in your model you haven't captured, and therefore please go and add X squared. Okay, if you had X alone, you may need to add X squared because your model adequacy doesn't show that your model is adequate. And the U shape is saying that, look, you may have a quadratic term that you are missing. So this is how we check some of the model adequacies. Okay, it's 231. I like to end here. It is the most important part. And let me talk on influential points, and that's it. We are saying that be careful also about influential points. Sometimes when we are studying things about West Africa, Nigeria tends to be an outlier. Okay, so sometimes one way is to take away Nigeria from your analysis. Study every country in West Africa and see the result. When you are done, plug back Nigeria and compare whether Nigeria has systematically changed your result. Okay, so that's the idea of influential point or outliers. An outlier is a point that is far off from the other point. Look at this point, so far from the others, and outliers can mislead your result. So that's what I want to comment on in the next 2 minutes, and then we take a break for 5 minutes and we move into state or application. Now, so forget about this outlier. Look, forget about this. If this does not exist, then you will see that the line should have been positively sloped. Look, the line of best fit through all the points would have been positively sloped. That means your beta would have been positive. But because of only one influential point, an outlier here, outliers are influential, so they drag the line of best fit towards them. So this outlier has dragged the line towards it, causing us to have a negative slope. Whilst in its absence, it should have been a positive slope. So that's how powerful outliers can mislead you. We have a negative line here, something which could have been just positive. So your model is sensitive to only one guy. How can you make inference or policy recommendation when only one guy is driving the direction as negative? So in this case, you might be careful. You might want to drop this outlier or state it in your conclusion that if an outlier is actually real, like Nigeria really exists, then you do the sensitivity analysis and say, look, when I take off Nigeria, beta is positive. But when I add Nigeria, the beta is negative. Looks like we're probably going to go with a positive slope. Okay. Otherwise, you mislead people. But if an outlier, a data which is different, far off from the others, is from a mistake, then you can look to correct the mistake. You can call the people and say, oh, what is the size of your farm? He had said 100 acres. Meanwhile, it was 10 acres. Then you can correct that. If it is a recording error, you can also correct that. But you cannot throw away an outlier which really exists, like Nigeria. It really exists. You cannot throw it away. You can do the sensitivity analysis. So be careful of outliers and so on. Okay, I'd like to stop here and move to the application if there are no questions. I sent a practice document through WhatsApp. This afternoon, I emailed last week's video and some data. So I'm going to move to some discussion. The next 1 hour, we are done. It's 2:35. I will continue at 2:40. Okay. Any questions? If not, we'll pick up at 2:40. Any questions?
I have a question, please.
Go ahead.
Please, the outlier, the influential point.
Yes.
If you look at the illustration, because we are told that to draw a line of best fit,
yes,
to pass through majority of the points.
That's right.
But this one, I don't understand why the outlier is actually pulling itself towards itself instead of, we have about 5 other points that are similar that we can even draw the line of best fit through them. But I don't understand it.
Okay, thank you. That's a good question. So were you here the first day? Have you missed any class?
No, I've never missed.
Excellent. So you will get it quickly. Now, the story is as follows. If you were manually drawing it, you had plotted your scatter plot. Manually, you were doing, then you will know this is just off. And then you manually just probably think of this as the line of best fit, and you record a positive slope, and you are gone. But you see, we are using a software. That's 1. And 2, remember the least square estimators? Remember the ordinary least square? Do you remember how we derive them? The concept is that we are minimizing sum of square error. Do you remember? Now, one was the question. Do you remember the idea behind our estimators is to minimize sum of square residual?
Yeah.
Yeah, so that's the idea. So this one is the farthest. So the line wants to come closer to it to minimize the error. Okay. So it will not do this. When it does this, it has created too much of a distance from this guy. It's too far. So we are minimizing some of the squared residuals. So this line here, you see, look at the gap here. It's not too bad. Here to here, it's not too bad. This is not bad. This is here to here is not bad. From the line to here is not bad. From the line to here. So it is by construction, the way the estimator is designed, is supposed to minimize the distance it has from all the points.
Yeah.
That is why outliers drag the line to themselves. because they are too far off. So if it had done this, then unbelievable, the gap will be too wide.
Yeah.
So by construction, the ordinary least square estimator is supposed to minimize sum of squared residuals. And because outliers are too far off, the line in an attempt to minimize that gap will drag itself towards that point. Okay. So that is the effect of an influential point. Okay. I hope that helps.
Yeah, thank you very much.
Awesome. So folks, we'll start at 240. Meanwhile, where is the practice test? Meanwhile, I want you to be reading. The document is in your WhatsApp group I sent to the course rep. You can be reading it. Those of you who have it on your phone, you can bring it up. Do you guys have any class after this?
No.
No, doc.
All
So
right,
please, some of us have class.
okay, we'll see. What class do you have?
Doc, please, we have a population genetic class after it.
Okay, fair enough. All right, folks, it's 2:40. Let's discuss question 1 and question 3 quickly within the next hour. If there's time, we discuss at it. Question 1. Someone should read for me, please. Read for us. Okay, volunteer. You read for us.
The problem of interest to health officials is to determine the effects of smoking during pregnancy on infant health. One measure of infant health is birth weight. A birth weight that is too low can put an infant at risk for contracting various illnesses.
Please match your voice more.
These factors, other than cigarette smoking, that affect birth weight are likely to be correlated with smoking. We should take those factors into account. For example, higher income generally results in access to better prenatal care, as well as better nutrition for the mother. An equation that recognizes this is BWGHT equal beta 0 plus beta 1 cigarette plus beta 2 famine plus U.
Okay, that's fine. Thank you. So, how officials want to know the effect of cigarette smoking during pregnancy on the infant health? Okay, and birth weight is an easy way of telling the health of an infant, a baby. Okay. To study that, you specify. So, if our consultant and Ministry of Health came to me that, sir, we want to learn the effect of cigarette smoking. Recently, they are talking about effect of galamsey on your health, blah, blah, blah. So I can specify a model, regression model like this. The birth weight of the infant equals to beta 1, the number of cigarettes that the mother smokes, maybe a week per week, the number, the sticks of cigarettes. Okay, and this is family income. Family income. We have explained why family income matters. So we are explaining the birth weight of a baby. We know cigarette impact, the mother's cigarette smoking impact. So it's a relevant variable. Family income is relevant. We've explained that the higher income gives access to better prenatal care. which will subsequently impact the health or the weight, birth weight of the baby. Okay. Now, there is a, can somebody think of another variable which may affect the birth weight of a baby, apart from family income and cigarette smoking? Is there another relevant variable we've left out in this multiple regression?
The mother's health status.
The mother's health status. Yes, so we could have plus beta 3, the health status of the mother. So you include all this.
And then the BMI of the mother.
Yes, that could be put under the health status. Okay, we may run into multicollinearity as I mentioned earlier. Okay, but you can start with that. If it causes a
what about the age of the mother? The age.
The age of the mother certainly has a role to play, yes. But I don't know if we can put that under the health. So the health status variable the first person mentioned, you must know how it is defined. If the BMI might capture that and so on. So just find a nice variable. If not, you can include them separately, the age and so on. And later you do some careful study to see which variable is subsumed under another and so on. But those are all good variables you begin to think of. Some of them, the health status of the mother, you may not get that data. You may not. If you got that data from Kolebu, they may give you the health status and the age. They may not give you the BMI. They may have the weight. You may have to calculate yourself. So sometimes there are data constraints and so on.
What about the length of pregnancy? And then the gender?
Did you say gender? The gender of the baby? Hello? Hello? Can you hear me, guys?
Hello, Doc.
Yeah, can you hear me?
Yeah, we can hear.
Yeah, what is the gender of the baby?
And what about the nutritional status?
Yeah, Doc, we can hear you.
Okay. Yeah, so all those variables are great. When you are doing your thesis, that's when you narrow down and see which one is good. But all those you've mentioned make sense so far. Okay. Ex ante, before we move into any serious work. Okay. Please, let's answer the first question. What is the most likely sign of beta 2? Do you expect beta 2 to be positive or negative? And why? Oh, beta 2 has been explained already. What is the most likely sign of, what do you expect beta 1 to be? Even before you start the analysis, what do you expect beta 1? Should it be positive or negative?
It should be negative.
Negative. That means higher cigarette smoking will have a negative impact on the weight. Excellent. And we expect beta 2 to have what?
Hello, Doc.
Yes.
Positive. It can either be positive or negative.
You said beta 2 could be positive or negative. That's a good one. Why could it be negative?
Negative if the income is very low, and positive if the income is very high.
Yeah, but we are looking for overall. So
overall.
So you tell yourself, you ask yourself,
it should be positive.
Yes, ask yourself, if family income increases, what happens to the birth weight?
It will be positive.
And if family income decreases, birth weight
Then
go down.
Also
so
decreases.
That's still a positive relationship.
Yeah.
Yeah. Up, up, down, down is a positive relationship. They are going up together or they are coming down together. Those are all positive relationships. So excellent. So when you go to the data, you see whether you got a positive or not. Then you begin to interrogate your results. So let's go to B. Do you think cigarette smoking and family income are likely to be related? Explain why this relationship could be positive or negative. Any attempt? Why would the number of cigarettes a woman smokes during pregnancy be related to her family income?
No, please, the A part, I didn't get it well, sir.
Okay, we said what is the most likely sign of beta 2? How do you think family income will be related to the birth weight of a baby? are they going to have a positive relationship or negative? That's what we're asking. If your family income is more, what happens to the birth weight? Will it be more?
Yeah, it can be more.
Yes. If you believe so, then you say it's the beta 2 is likely to be positive. But if you think that is up to you, some of these things, there could be no right or wrong as long as you can explain. But there are some that appeal to common sense. So here, the one who has the question, is it okay? Is it clear?
Yes, I'm clear, but looking at the beta naught, which is expected to be negative, but I was thinking that that would also be positive.
Which one?
The beta naught.
Beta naught is expected to be positive for sure.
Yeah.
Did I say
Beta naught is intercept. That is the intercept.
Yes.
Yeah.
Yeah. It's beta 1 that we are saying is negative because the woman is smoking.
That's right. Beta naught is the average weight of a baby, whether there is family income, whether there's no, even if there's no family income, if there's no cigarette involved, on average, we expect the birth weight to be beta 0. Is that okay? Can we move on?
Yes, please. Yes, please.
How do you think cigarette smoking and family income, how are they likely to be related, positive or negative? Do you think they are related at all?
Yeah, they can be related.
Yeah, please explain.
This is because if she doesn't have money, I don't think she'll be having that amount to spend on cigarettes.
That's right. That's right. And you expect them to be negative, positive, right? The more money, the more cigarette, or what?
Yes.
Yes, sir. Yes, sir.
Yeah, that's all. We can move on. There is part C. Now estimate the equation with and without family income using the data birth weight. Usually I'll supply you the data. Report the result in equation form, including the sample size and the R squared. Discuss your results, focusing on whether adding family income substantially changes the estimated effect of cigarette on birth weight. So I'm going to go to my program. I use data. You can do this in Excel. You can always go to YouTube and ask on YouTube how to do regression in Excel. Look at it and you can do it in Excel. If you use R, Python, whatever, the computer science, you can do whatever for the take-home exam. Okay. So I'm going to my data and run this regression. Those who use data, you can write down my code. Okay. So can you see the program now, the software?
No, please, Doc.
Not yet.
Can you see now?
Yeah, we can see.
Yes, please.
The data is birth weight, right? Yes. So I've loaded the data, okay? I can describe the data for you to see. So I just type in the code, describe here. So when I hit enter, it will describe the data. Okay, we have family income. Then you know, 1988 family income in thousands of dollars. Cigarette tax, cigarette price. This is birth weight. It describes the data. There is a variable called male. And what does it mean? It's equal to 1 for a male child. That means 0 for female child. Okay. This is how we do regression in data. So regress, was it birth weight? If you look at the cursor, I can either click here to bring the variable, or you type it the way it's coded, birth weight. You can type BWGHT. So I'm regressing birth weight on cigarette. You must type them exactly how they are coded in the data. So you can pick them from here, the left-hand side here. So we are supposed to regress birth weight of a child on the amount of cigarette the mother smoked. After that, I'll add family income. So let me do just this. I'm going to hit enter. So reg, you can spell it in full. okay? But there are shortcuts. So regress birth weight on cigarettes. I hit enter, and then I have results. So we'll focus here. This is the result. Okay. Please mute your mic. The question said report your results in equation form. So you write this birth weight. Please take note, because when I give the exams, I will also say report your result in the equation form. So this is what I mean. We have just estimated birth weight. So this, like the predicted birth weight of a child is equal to, and if you did it in Excel, you have the same result. Please, this is the constant, okay? This is the beta zero hat, estimated beta zero, constant, cons. So 119 point something, maybe 77. I can shorten it. Plus, no, minus, then the cigarette is negative, right? Minus 0.51 is the equation form. You report your result. I'm picking the beta 1 hat now. I just wrote down the beta 0 hat. Now, beta 1 hat. Negative 5, 1. You can shorten it. Okay, that's all. You don't write the error term because it is estimated to be 0. The error has a mean of 0. So when we did do the estimation, we assume it goes to 0. So that's all. I'm done. Oh, this is 6. 6 cigarette. So that was the beta 1 attached to the cigarette. That's all. I've reported the result in equation form. That means that one more stick of cigarette smoked reduces the birth weight of an infant by 0.513 pounds. Okay, the US uses pounds. If it's Ghana, then it's a kilogram. That's all. You see, oh, holding other things constant, one more cigarette smoked per day. Look at this. Look at my cursor here. 6 is cigarette smoked per day while pregnant. So one more of cigarette smoke per day while pregnant reduces birth weight of an infant by 0.51 pounds. Okay. Is that okay? So this I've reported in equation form. Then let me do the inference here quickly. Remember, did any of my colleagues teach you p-value? P-values.
Yes.
So with this p-value, you reject. If we were testing this variable, cigarette is significant, it's statistically significant. In fact, look at the t statistic. The absolute value of t statistic is 5.68. This is t calculated. 5.68 is greater than the table value. If you were to go on the table to read the t alpha, 5%, blah, 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 you get 1.96. The critical value will be 1.9 at 5% alpha level. So this t calculated, its absolute value is greater than the table value of the t. Therefore, we reject the null hypothesis and conclude that this variable cigarette is statistically significant. In fact, the p-value is 0. Okay, you said my colleague taught you a 0 p-value means you reject the null hypothesis. So the null hypothesis is cigarette, the coefficient of cigarette this year is 0 versus it's not. So this one says what? This was beta 1. Beta 1 is the one here. And we found some beta 1 here. Whether it is statistically, this is beta 1 is 0. We say cigarette is irrelevant when we talk of the birth weight of an infant. That's a null hypothesis. Cigarette is irrelevant or not significant. And here we have that the p-value is 0, so we reject the null hypothesis and conclude that cigarette smoking is significant. In this case, our null is like this. Sorry, our alternate is not 0. Our alternate, we reject the null in favor of the alternate. So you say cigarette is statistically significant. Okay. Any questions here?
Yes, Doc.
Uh-huh.
I just want to draw us back a bit. This p-value and null hypothesis, I'm still not understood it, to be frank. I don't know if you can spend just like 2 minutes. Where did we state, for me, where did we state that the null hypothesis is, I don't know, because I don't see anything, but you are just saying we reject and we accept. Just 5 minutes, I beg colleagues, because I've never understood it till now. I don't know if it's possible. If not, we can just keep as well. And also the data, is it something you're going to provide later on? And as you said in the exams, are we coming along with PCs, or how would that be handled?
So the last question, the exam is take home. It's take home, and we will supply the data. So you have data, but you look for whether you are using Excel, the program you are using, then you can do it yourself. And somebody will supply the data. Okay. Yes. Now, p-value is not, you have to be taught well to really understand it. It actually takes time. Okay. I thought one of my colleagues taught it, but you are saying you didn't understand. It takes time. Now, over here, last week, were you here? I did inference. Okay, last week I did inference. Were you here? Is it still last?
Yes, Doc. Last week, unfortunately, I couldn't make it. I'm saying it will take time. I mean,
yeah, we did part of inference last week. That's why all of a sudden I'm doing hypothesis testing here. Okay. After you have regressed, after you have done your regression, it's possible cigarette is not relevant when we are talking about the birth weight of a baby. You included cigarette in the regression because you are claiming cigarette is useful. Cigarette variable is relevant when we are explaining the birth weight of a baby. We have also said family income is relevant. All those variables you claim were relevant. After the analysis, you come and test them, whether they are indeed significant or relevant or not. That is why after the analysis, we are going straight to hypothesis testing. Inference. Okay. This, I assume I'm talking about, this is beta 0 and this is beta 1. So we are testing whether beta 1 is actually 0 or not. If it's 0, it means cigarette is not useful in explaining the benefit. If it's not 0, then it's an important variable which should stay. So how do I know if it is significant or not? That's hypothesis testing. And we use these p-values and t-statistics. Okay. Actually, my colleague who taught this, we gave him like 4 Fridays. Okay, so I thought he did a good
Doc, she did. She taught us, so maybe he has a difficulty.
It takes time,
But she did.
If you like to come next week on Zoom, you guys, I can meet again and do some of these things. But p-value is defined as the probability of obtaining an extreme observation as the one obtained if H naught were true. And that's a technical definition. That's a technical definition. So let me try. The probability of obtaining an extreme observation as the one obtained if H naught were true. And now we reject if that probability is 0. If that probability, you are supposed to manufacture Nkatia burger. Nkatia burger has a lot of air, right? Maybe there are some non-Ghanaians, so I shouldn't say Nkatia burger. Maybe you manufacture electricity bulbs, and you supply 10 boxes. They use them, they found 10 pieces of the bulbs to be defective. And somebody says, your company is useless. They don't supply better bulbs. Then you say, no, you want to test, collect some data and test. So maybe out of the 100 boxes, 10 of the boxes were bad. Okay, 10 were bad. Out of 100, 10 were bad. Out of 100, 10 were bad. Out of 100, 10 were bad. Is that not 10%? Out of 100, 10 were bad. You found 10 to be bad. So the p-value comes that what is the probability of obtaining? So the null hypothesis probably says none of the boxes is bad. This is the company said they are smart people, they produce better bulbs. So this is a null hypothesis. None of the bulbs is bad. That's a null. None of them is bad. Null hypothesis. That's a status quo. The company insists none of them is bad. You took a sample of 100 boxes, 10% were bad. P-value comes in. Okay. What is the probability of obtaining? What's the probability that 10% of the boxes will be bad? If the manufacturer says none of them is bad, that is what p-value is doing. Given the H0, the company says none of the boxes is bad or defective, but I have found 10% that are bad. Okay, what is the probability of obtaining 10% bad bulbs if the manufacturer insists none of them is bad? That's what p-value is doing. So look at this. A p-value of 0 means what? So the p-value is 0 here means that the probability of getting 10 boxes out of 100 being defective is 0. That means it is not possible to get 10 boxes defective out of 10. That's the p-value. If p-value is 0, p-value is what? What's the probability of getting 10% defective if the manufacturer says none is defective? And I got p-value of 0. Probability of obtaining, what's the probability of obtaining? So the p-value of 0 says I can never get 10 boxes that are defective out of 100. If the manufacturer says none is defective, it may be confusing, but it is like we are using logic. Okay, we are using logic. P-value of 0 says you will never find 10 boxes. You can never find. That's the meaning of p-value of 0. That if indeed none of the boxes are defective, you can never find 10 of them. That's p-value of 0. Probability of that happening is 0. I can never find. Then I said, oh, but I have just found 10 of them, so I reject the null. I reject the company's argument. So that's the idea. Okay, the p-value is 0. You mean I can never find 10 boxes, but sir, I just found 10 of them, and so I reject your null that I can never find 10 boxes that are defective, given that all of them are good. Okay, so it's a bit technical. You will need a lot of explanation and examples to get. The computation is easy if you are doing the mathematics, but this is the flavor of the logic behind. Okay, so this is my attempt for now. In the future, I don't know. But yeah, if you ever need it in your research, you can stop by. I'll be happy to help you. Okay.
Hello. Hello.
Hello.
Please, how would you use SPSS to deal with the same problem?
Yeah, that you can. I don't have SPSS right now on my laptop, yes, but it's easy. It's easy. SPSS involves clicking. So that actually becomes easy. You go to, I think, statistics tab, and then you drop down, you click regression. It's actually to put your Y variable, you put the birth weight. It's actually to put the X variable, you put the cigarette, you hit enter or something, you click run or something, then it provides the result. Okay, you can just go to YouTube and Google search how to do regression SPSS. You will see one demonstrated, straightforward. Okay.
Do you have options for linear regression and then multiple regression?
Multiple regression is also linear regression. Yes, there's option there.
Okay.
Yes.
Oh, all right. Thanks.
Option is there. So folks, let's wrap up this. The question said we should add family income. So I'm going to add family income. I've just added it. Now we have a multiple regression. So when I hit enter, the result will come. So this is it. Cigarette initially was negative 0.5. It's now negative 0.4. That means when you were doing simple regression, when you ignored a relevant variable, family income, you were probably exaggerating. You said 0.5, but it's actually 0.46. So this is demonstrating that when you omit relevant variables, you may have biased result, or your result may not be consistent. If you were recommending to the Ministry of Health, you would have told them that it is 0.5 reduction in the birth weight, but maybe it is actually 0.46. And in terms of weight, the small differences matter. So the point here is that please include all relevant variables. Don't just include your main variable. You may not get consistent result. Over here, p-value of 0 means cigarette is significant. This is almost 0. Family income is also statistically significant. Okay. So here, if family income were to increase by, let's say, $1, then the birth weight will increase by 0.09 pounds, something like that. Is that okay? Is that okay?
What about the equation for this?
Yes.
The equation for this.
Yes, please. You take the constant,
yes,
the family, then the cigarette.
Yes. So the equation I'm trying to erase is you just add the family income part. Like you put the 1.1, this becomes 6 something, right? And there's a 9.7. Yeah. Then this is negative 0.46. Negative 0.46. Okay, so it's straightforward. Plus 0.0909 family income. That's all. So we have 20 minutes. That's all. It's all right. Can we move to the next one really quick?
Okay, Doc.
Yes.
So in this case, not holding all other things constant.
No, holding other things constant. Holding other things constant. One more cigarette smoked per day decreases the birth weight by 0.46 pounds. Holding other things constant, $1 increase in income increases the birth weight by 0.09.
Okay.
All right. Let's take one application and then we go. It can be done in 20 minutes. Please, somebody should read this for us very quickly.
The data in the
loudly.
The data in the FERTIL2 include, for women in Botswana during 1988, information on number of children, years of education, age, and religious and economic status variables. A. Estimate the model. Children require beta naught plus beta 1 education plus beta 2 age plus beta 3 age square plus U by OLS and interpret the estimates. In particular, holding age fixed, what is the estimated effect of another year of education on fertility? If 100 women receive another year of education, how many fewer children are they expected to have?
Excellent.
Hello, Doc.
Excellent. I'm trying to load the data and then we practice. So there is something we call fertility in the labor economics literature. Where is the question? Right here. So this is the data for women in Botswana. Children. The number of fertility. Fertility is not about whether a woman can give birth or not. In the literature, fertility means the number of children a woman gives birth to in her lifetime. The number of children a woman gives birth to in her lifetime is called fertility of women. Fertility of women. Now, we all know fertility of women depend on the amount of education, their age, and so on. Okay, over here we include age squared because as a woman grows, she's able to give birth, and at a point, age may have a declining effect on the amount of children. So because of this curvature, the age square was included to capture it. If you don't include the age squared, you are assuming the relationship is forever, up, like this. Children and age, you are assuming it goes up forever. But because we know as the age advances, it has negative effect on fertility. We capture that with the declining. So age can help you increase fertility, but can have declining effect. That's the purpose of the age squared. So in your research, if you suspect some relationship like that, you capture it like that. Okay. Now, so that's fertility. So let's go and run it. When I go to the program, remind me, we are doing children on education, age, and age squared. So we are regressing.
Hello, sir.
Yes. Can you see the data program?
Yes, sir. Please, I have a question, especially on the age squared bit of it.
Sure.
Yes, my issue is looking at the equation. Look at the equation. If you have age and the same parameter, you are squaring it. If I look at it plainly, I don't see how it affects the dependent variable in the sense of reducing it. Because when you have a variable and you are squaring, I thought it rather increase it.
Oh, we are capturing a relationship, like I said. We are capturing a relationship. For example, we have the number of children and then the age. If you have a graph of children on age, a graph of children on age, we are seeing a relationship. When you plot a graph of the number of children a woman has as the age increases, we are seeing you are likely to see something like this. Do you get it?
Okay.
That, as the age increases, she's able to have more children. Maybe if this is age 0, as the age increases, she's able to have more children. But as there's a point, maybe after maybe 40,
that it will start declining.
Okay,
so that will be the maximum. Then it starts to decline.
Yes. So if you have such a relationship, you capture the curve using the age squared.
Age squared. Okay, excellent. So I've got it. Thank you very much.
That's a quadratic. Okay. So please see there. We have about 40 minutes. Can you see the code I've written here? I'm regressing the number of children a woman gets on her education, age, and age squared. Do you see that? I'm going to hit enter and then we see the result. There's an error because I didn't put a E here. Okay, so we have the results here. Okay, p-value is 0.0000 here. So they are all statistically significant. Now, education has a negative effect on the number of children a woman gets. Does that make sense? The more education, the less children. You believe that?
Yes.
Yes. The more years of education. Then age has what? Positive effect.
Positive effect, yes.
Okay. Then we have a constant. Okay.
Doc.
Yes.
Wouldn't age have a negative effect?
Well,
I think it's two ways. It's two ways. If a girl is young, yes, the probability is low, and when a woman too matures to a certain age, the probability is also low.
Yes, I agree with you. Okay, you are running into something technical, but you see this is h square, right?
Yeah.
You see that here is negative, right? In core mathematics, once the x square has a negative, then it looks like an N shape, right? Once I put the negative here, it becomes N shape. And when I take off the negative, it becomes U. So the negative confirms the idea that we are expecting something like this.
Yeah.
So it's kind of, well, initially, as age advances, you can increase fertility, and later as age advances, it declines. I think that is a stylized fact. Okay, but your argument also makes sense. Okay, stylized fact means something that is generally true, although somebody can have a counter example. Okay, so it's kind of a stylized fact. Somebody says, don't go to America, you can make it in Ghana. And he will point to despite. But somebody say America is always better than Ghana. That's like a stylized fact. On average, it may be better than Ghana, but somebody can find a counter example. So I think it's generally okay. Okay, so my sister, I hope that's fine. Is that okay? The one who talk of who discuss the lower, like younger case stuff. Is that okay?
Our sister.
Is that okay? The lady. She's probably not here. Is anyone with me? Oh, I lost.
Oh, sir, I wanted to have a look at the question.
Yes, Doc.
Yes.
Hello, sir.
I
wanted to have a look at the equation, please.
The equation.
Yes, please.
Which equation? The results.
Yes. Yes. Yes, I wanted to capture it.
Oh, you can take a picture quickly and then we move.
Okay, please, a minute. Screenshot.
Okay. And this video, this is recorded, right? So you can always.
Okay.
watch.
Okay.
That's fine. Just take a snapshot. There's something I have to say. I don't know if I said it. Okay. So watch here, folks. Over here, look at this. If education increases by, if somebody goes to school, there is a feedback. If somebody goes to school one more year, a woman that goes to school one more year will have 0.09 fewer child. 0.01 fewer child is not interesting to say. How can you present statistics to people as 0.09 fewer child? They don't know how to appreciate that. That's why the question went ahead to ask you this. Okay, please, we're out of time, so follow me closely. Look at this. If 100 women, that 0.09 fewer children, it doesn't sound well in statistics. We are talking of human beings and you are talking 0.01 fewer child. So the question is, if 100 women receive another year of education, how many fewer children? So you multiply this by 100 now. So if one woman goes to school, there will be 0.09 fewer child. But if 100 women go to school one more year, there will be what? 9 fewer.
9 children.
So this is how you present your result to policymakers. You think of it in hundreds because you're in individual terms, you are getting fractions of human beings, which doesn't make sense. During the COVID, they will say Ghana has tested 600 people per 1 million of the population. It's a similar idea that if you do the mathematics, they will say Ghana has tested 0.00001 human being per 0.01 human being. It doesn't make sense. So they multiply by 1 million. And you'll be hearing things like Ghana has tested 600 people per 1 million of the population. Okay, on average. That's our testing rate. They divide the number of tests by the number of Ghanaians. They get so many 0.000. The number of tests you have done over the 30 million Ghanaians, you get so many decimal points, which is not nice to convey. So you multiply by 1 million. Then it erases a lot of the zeros. Then you have a concrete number. Then Nigeria can do same. Then you cannot compare Ghana and Nigeria and say we are testing more than they are because now we are working in 1 million. So that's the idea here. I hope it makes sense to somebody, but I'm kind of right.
Yes, sir.
So let's look at the last bit. Let's look at the last bit here. We are asked to add binary variables, electricity. So whether a house has electricity or not is what? A dummy variable, yes or no. Whether a household owns TV or bicycle, these are not quantity. We just treated qualitative. So you create a dummy variable, yes or no, yes or no. Okay, we are supposed to add them. So I'm going back to the regression. I'll add electricity. Okay, please remember electricity, TV, and bicycle. We believe that this is a rural data. So possession, a household possessing TV, electricity, and bicycle may affect fertility, the number of children they have. So we go and include them. It's a rural area. So the question says we have to include them and interpret the coefficient on TV and explain why television ownership has a negative effect on fertility. We are going to add TV, electricity, and bicycle and explain why television ownership has a negative effect on fertility. Television ownership. Okay, let's do that and end. We have 6 minutes. So
interesting.
I recall the model right here, and I'm supposed to add, what were the variables again?
Television.
Electricity, television, and bicycle.
Electricity. You must pick them the way they are spelled in the data, how they were coded. TV, and then bicycle.
Hello, Doc.
Hello.
Have those parts of the data been loaded into the system?
Yes, I have loaded the data already.
Yes, please. Okay.
Yes, yes. I can show you a cross-section of the data. Can you see?
Okay.
You can see.
Yes, yes, yes.
You see the electricity 111 for all the homes that have electricity. 0 if the house has no electricity. Same with radio, television, bicycle. Okay. They are coded 1010, whether you have it or you don't.
Yes, please. Okay.
Yeah. And then education. Okay. If you want to know all the variables, you must go and describe the data and see. Okay. So if you can see my code, I'm going to hit enter. I've just hit enter. So if 100 women were to have an additional year of education, there will be on average 7 fewer children. 7 fewer children. Okay. Okay. And age still has the N-shaped relationship. I'm having some feedback. Age still has the N-shaped relationship. Okay. Then, they said, you see that we had 9 fewer children. But now that we've added television, bicycle, it has come down to 7 fewer children. So again, if you omit relevant variables, you may be misleading the policymaker. You just told them 9 fewer children. But when the guy said, oh, you have omitted bicycle, TV, electricity, go and add them to the analysis. When you added them, you now come back and tell him 7 fewer children. So be careful not to leave out relevant variables. Okay, and there's another way we can validate this result. We had 7, we have 9. We had 9, we now have 7. It can keep bouncing around, but there's a way you can pin down what we think it is for sure. That is beyond the scope of our discussion here. But for now, this is okay. Okay, the ordinary least square is fine. So please, let's discuss this and go. Why does television ownership, why does it have a negative effect on fertility? Any suggestions, folks?
Hello, Doc. Yes, if you are busy watching TV, you are not likely to engage in an activity that may lead to pregnancy.
Okay. Yeah.
Yes.
That's a good one, the traditional one. But that's not what
that is an experienced man talking.
That's not what I would take as the answer. I've had some funny answers in the past. Some students said, some of you are experienced a bit. So, you know, in the past in Ghana, people will knock on the door and they want to watch TV. when you have TV, so you are the only guy, people. So some of my students have said, oh, when visitors or guests are watching TV, then some of them leave in the night. By the time they leave, you are also tired and you just fall asleep. There is no room for having children, right? Those are crazy, answers I've heard in the past. But who wants to attempt an answer that I will give 100% to? The other one is fine.
What I would say. What I would say is that it decreases the desire to have maybe sexual relationship.
Television ownership.
Since you are occupied.
Yeah. That has been done already. Yes. Yes.
TV has an educational effect, and so such as family planning and all
Excellent.
that. And so
excellent.
It can have an effect.
Yes. So when you own television, you are likely to read about contraceptive. Okay. You have television. You can read up. You can listen, as you were saying. You watch programs on contraceptives, on family planning, and so it might help. But this one and the entertainment one they are all fine, correct answers. Okay. Last one. Why does bicycle ownership increase fertility? Bicycle ownership has a positive effect on fertility.
Yes. Hello, Doc.
Yes, why?
Yeah, I think bicycle ownership gives the owner the ability to exercise more, and the more you exercise, the more active your system is, the more energized your eggs and your sperms and reproductive rates are.
Interesting. Any other? That's a good one. Any other?
I also heard that if normally if they want a woman to be fertile, they normally, for the old times, they make sure they stop you from riding bicycles and doing vigorous exercise. They believe that it prevents you from getting pregnant. I don't know how true that is.
So that's a negative effect, right?
Yeah, is that not negative?
Yeah. So,
and Doc,
yes, Silas.
Sorry, Silas again. You see how I just joined late, but this positive and negative thing, I mean, at a go made sense, and I'm catching up. It's the same thing about the p-value. I mean, I'm not saying the other gentleman, sorry for it. I'm not saying the other lecturers didn't teach. They taught, but I'm not grasping it. That is why I'm just pleading with you to have explained. So for the other gentleman to have said, I didn't say they didn't teach. Okay, they taught it. But the understanding is what didn't come. But this one is easy to relate. I believe his background is in that area. That is why he's able to relate much better. But for me, I'm struggling. That is why I just was pleading. So that is just for.
Now looks like you all need it, right, in your research. All of you, right? You are in CBAS, so you might need this at a point.
No, hello, Doc.
Very much.
Hello.
Hello.
Yeah, Silas, I wasn't meaning, bad. What I was just trying to say was that it was taught. I mean, when you was asking, there wasn't response to that effect. And it will not speak well of us if somebody has taught something, then, another lecturer asks, and we are all quiet as though it wasn't taught. So that was just my point. I wasn't saying maybe. Yeah.
Yes, but I mentioned that the man, even the two of them.
It's okay, Silas. I have 0 minutes left. Actually, negative. So the bicycle ownership, some people say it serves as ambulance in the village. So the guy with the bicycle has more children. And a whole lot of interesting things. I don't know, but I will give you an interesting data for your take-home exam, and you will enjoy these things. Okay, so that's it, folks. That's the end. Congratulations. You are done FASC702. We will send the take-home exam through the course rep. You solve them and submit. Usually, they want you to submit yourself. Don't give it to somebody and so on. Okay. All right. Thanks.
Where are you submitting them?
Oh, you submit to my office.
Doc, the mode of submission now.
Yeah, they will all be clear on the exam. Okay.
But Doc, these were the questions, so I go to change them again.
Okay.
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 What do you say?
I thought these were the questions you were giving us.
No, I might repeat some, but
I beg, some of us we are struggling. Give us this one.
Yes,
If you change and pay wahala.
Dog, I tend to agree with him. Don't make it hard, because
See? See?
Hello, Doc.
hello.
Hello, Doc.
Hello.
Hello, Doc.
Hello.
Please, some of us, it's difficult for us to get this analysis too. I am pleading that if you can give us, if
all
you
of
can
us
pass it
agree
through.
with him. All of us have agreed, Doc. We are pleading.
If we can pass it through your system and maybe give it to us, then we do the interpretation.
Oh, no, you have to do one or two. You have to do one or two in Excel or your program yourself. You know, they even say we don't teach people well here. They can't do work in the industry. They can't do hands-on things. So there should be a hands-on, something applied. You do it. And if you interpret, you might not know how to do it. So you just do one in your lifetime over here, and that's it.
Yes, Doc, we agree, but don't give us the hard one. Give us the simple one.
Course rep has that document, the one I just did, and he has the data in his email. Begin to solve them. When I bring in the exam, then you just put them together and submit. Okay. So I'll look at that document to make the exam as you have appealed.
Thank you.
Okay. All right.
Please, you said you have sent me the data to.
Yes, I've emailed to you.
Thank you.
I've emailed them to you like 2 hours ago.
Okay. All right, Doc.
All right, let's start the
Oh, God bless you.
All right, good.
Dog, I'll call you.
Sounds good. All right.
Goodbye.
Okay, bye. Silas, please call me.
Yes, your number. Leave me your number, please.
The course rep has it. Just WhatsApp me.
Okay, sure.
Yes, Silas. Just me, I'll send it to you.
Okay, Claudius, please do it.
Please call me.